And everything.
Well, thank you very much. So first of all, I would like to thank you very much for the invitation, and I'm extremely happy to be here. I'm going to give some introductory lectures on Koszul cohomology in relation with algebraic geometry. And let me start with some motivation for introducing and studying these objects. So the motivation comes actually from projective geometry. So everything will happen over complex numbers. Of course, many of the results will be true also in positive characteristic, but some of them fail in positive characteristic. That's why I'm going to focus on complex numbers. So in general, if we consider a projective variety, we can associate to this variety, of course, the two algebraic objects, the first of which is the homogeneous ideal, and the second, if we just put S the algebra of polynomials, where C, the second is just the homogeneous coordinate ring of this variety X. And we are interested in qualitative study of these objects. Like, for example, what is a minimal system of generators for this IX, or what are the relations between these generators, and so on. So all these questions, or trying to answering these questions, amounts to studying the minimal resolution of the homogeneous coordinate ring, which is the following. So we have an exact complex. Here we have S, X, here we have S. Here we have some, let me stick to the same notation. We have some direct sum S minus Q, and here we have some powers, beta 1Q, direct sum S minus Q, beta 2Q, and so on. So these are free graded modules over the polynomial ring, and minimal means that all the entries here, so here we have basically matrices. So all these matrices have, so the elements in these matrices are homogeneous polynomials, but we require that these entries are not non-zero constants. Okay. So we can actually rewrite this. Every direct sum S minus Q beta PQ. So this is at the position P, and the sum is taken over Q. We can write it as a direct sum S minus Q tensor some finitely generated vector space over complex numbers. Okay, why would we want to do that? Because, for example, here we have, I mean, in the first step here, we can read the generators of the ideal. And the second step, we can read the relations between these generators. And here we have the relations between the relations, and so on. So this is somehow, this is the somehow the expression of this qualitative study we want to perform, and we were talking about. Another interesting thing is that out of this minimal resolution, we can recover the Hilbert function and the Hilbert polynomial of this variety. And this is actually the way we can prove that the Hilbert polynomial actually exists, and it's a polynomial. The existence of the Hilbert polynomial can be seen as a consequence of the existence of this minimal free resolution, which is known to end after n plus 1 steps by the Hilbert-Syzygic theorem. Okay, and just a word of warning here. The minimal resolution depends on the embedding I mean, if we take two different embeddings of the same variety in the same vector, in the same projective space, we can get different minimal resolutions. Like, let me just give you a silly example. If we take 3 points in P2, so let's call this X, P0, P1, P2. So basically 2 things can happen here. The first possibility is that the 3 points lie on a line. So that's the first case. And then if we look at the ideal, we will see that the ideal is generated by a linear form, which is this line. And we need another cubic. Sorry. And so the cubic will cut out the 3 points on this line. So the ideal will be generated by the line and a cubic F. And if we take a closer look at these two forms, we will see that there is only one relation between them, which is the trivial one, LF minus FL equals 0. That's kind of silly, but it's true. It's a relation between these two. So then in this case, the minimal resolution would look like, as here we have S of X, 0. Here we will have S of minus 1 plus S of minus 3. That's just the line and the cubic. And here we will have an S of minus 4 at the end. So, and the second case, of course, is when the 3 points are not collinear. So please allow me to take the points as being the coordinate points. 0, 1, 0, P2, 0, 0, 1. And then if we P0, P1, P2, if we look at the ideal, we will see that the ideal is generated by 3 quadrics. Which are x1, x2, x0, x2, x0, x1. So on the figure here, so the first one is just these 2 lines. If we intersect with the other 2 lines and the other 2 lines, we will get exactly the 3 points. And we have, so let me call this just Q0. This is Q1. This is Q2. And we will have exactly two relations between these 2 quadrics, 2 independent relations. Which are, if we multiply the first one, Q0 by X0, we will get just X1, X0, X2. And we can do the same for the others. So X0, Q0 minus X1, Q1 equals 0. X0, Q0 minus X2, Q2 is 0. And the other one is just a combination of the 2. So we have these 2 relations. And then the minimal resolution is the following. So here we have S. Here we have the 3 quadrics, and we have 2 linear relations between these two quadrics. So we see that the minimal resolutions are quite different, whereas the Hilbert polynomials are the same. So first and second case have the Hilbert polynomial is constant, equal to 3. So somehow this minimal resolution is manages to detect more information about the variety than the Hilbert polynomial.
Sorry.
Yes?
Second relation is x1 and 2,
It's the same. I mean, we can take x1, q1. I mean, sorry, yes, this is q0. Or x1. Yes, thank you. Okay, and that's we can also do this the similar thing. So if M is a graded S module which is finitely generated, which implies, by the way, that it's also bounded in degrees from below. We also have a similar minimal resolution. So here we have M, but instead of S, which was the case for homogeneous coordinate rings, here we will have just another free graded S module. And as before, we just can take this as being, this is just a number of, this is a vector space which counts the number of copies of every part. Here we have direct sum S of minus q, beta 1q, and so on. It will stop after n plus 1 steps. So it stops here. So here we have direct sum S minus q, m1q, and so on. The meaning of minimal is precisely the same, that we have no non-zero constant entries in the matrices. And again, the Hilbert polynomial and the Hilbert function can be recovered from this minimal resolution. And let me give you another example, which will be a very useful example, which is we take for M the residual field, which is S over x1, x0, xn. That's the irrelevant ideal. Let me just denote by V the vector space generated by the variables. And then we have a description of this the minimal resolution of this module, which is the first example of a Koszul complex in our context. So the minimal resolution is the following. I'm just going to give you this resolution. So here we start with our module. Then we have S. Then we will have the tensor S minus 1. Then we will have wedge to the tensor S minus 2, and so on up to the last step, which is wedge n plus 1 v tensor S minus n minus 1. And here we have 0. And the maps are the following. So the map from wedge p plus 1 v tensor S minus p minus 1 to wedge pv tensor S minus p is given by, here we take a multivector, which is x I naught wedge x I n. Tensor some polynomial will be mapped to, and what we do is just we take out one by one these variables x I naught wedge, here I j, we have nothing, x I n. So the meaning here is that we have x I naught up to x I j j minus 1 wedge I j plus 1 wedge x I n, and that variable we've taken off, we multiply it by p. And here we need to alternate this sum. It's up to p, sorry. So these are the maps, and the fact that it's a complex can be verified just by hand. You just write it down. It's a complex. It is minimal by definition, and it's exact because we have homotopy maps, exactness is due to existence of homotopy maps, and they go from, let's see, if we take wedge P V tensor let me just stick to some homogeneous component of this. So these are homogeneous polynomials of degree q plus 1. This goes to wedge P plus 1, right? V tensor SQ V. So this map will be given by xi1 wedge xip tensor some polynomial, homogeneous polynomial, will be mapped to the sum over k xk wedge xi1 xip tensor dq over dxk. So these maps realize a homotopy of complexes. Actually, exactness, proving exactness is the same as proving exactness on any degree. And fixing a degree, we if we fix a degree, then we just work with vector spaces. So these are complexes of vector spaces, and the identity, or a multiple of the identity, and the zero maps are homotopic because of that. So here we see is the first place where characteristic 0 is needed because of that multiple appearing in front of the identity. Okay, and what is this good for? So this complex we can also erase here. So that's actually useful for computing minimal resolution. So remember that our aim would be to be able to compute minimal resolutions. And how to do that? So if we just consider some module, some graded module over the polynomials, and we take the minimal resolution, zero q, we would like to be able to actually compute this resolution, starting with some particular module like this one, right? For this one, we were able to do it by hand. In general, how to do it? Well, first of all, let's remark that, so we all agree that if we are able to say something about these vector spaces, to compute these vector spaces, then we actually compute this minimal resolution. So the question is now how to actually compute these vector spaces appearing here. And now we use the minimality of this resolution. And minimality has nice consequences. Like, for example, if we twist this complex by the residual field, and all these arrows will become 0. So this will make all these maps vanish in the new complex. And the differentials become 0. And then actually these vector spaces will remain. So because of that, we can actually say that MPQ is just we take the Tor over S of M and this S over X0 Xn Tor P, because we are in position P, and this Q here, if we just take the whole direct sum, we will get the whole Tor. So actually every MPQ will be a graded piece of this Tor. So MPQ will be Tor P S M X naught Xn Q. So far so good. Now we know that the Tor functor has a very nice property, which is the symmetry. So Tor is symmetric. Which means that if we want to compute a Tor between two modules, we can either start with the minimal resolution of one module and twist by the second one, or to start with the minimal resolution of the second one and twist it by the first one. So the moral is that either we start with the minimal resolution of M, twisted by the way, this is over S, twisted by the residual field, then we get these Tors, or we can just resolve the residual field, take the minimal resolution and twist it by our module and get the same thing. And that's a kind of interesting because the minimal resolution of the residual field was computed here. So this actually means that this Tor M S X naught Xn Q can also be computed from, so we take this time, this resolution we twist it by M, so we will get, let's see, M0 V tensor M of minus 1 over C wedge 2 V tensor M of minus 2 again over C and so on. So these Tors can actually be computed from this new complex. So we can say that these Tors are actually the cohomology of these complexes in every graded piece. So the conclusion is that remark that we have a shift in degrees here at any step, right? So if we just compute in degree q, here we will have degree q minus 1, q minus 2, and so on. So the conclusion would be that MP p plus q, and here I replaced the second one by p plus q because of this shift in degrees, is the cohomology at the middle of the complex, of the following complex. We have here wedge p plus 1 V tensor M q minus 1, wedge p V tensor MQ, to wedge p minus 1 V tensor MQ plus 1, where the first map here is given by, it's very similar to that one. So we just take xi naught wedge, because it's actually deduced from that one, xip, tensor some element. This time is not a polynomial anymore. It's just some, I don't know, call it B. This is mapped to the same thing. Right? And here, MQ is just the P plus Qth graded piece of the module M of minus Q. That's why we have to take into account this, of M minus P, sorry. This shift in degrees. And this is how we, so that's actually the Koszul cohomology of M. So this space, this complex vector space is called the Koszul cohomology of M with values in V. So V was the space of variables, and it's denoted by KPQ MV. So just remember that these Koszul cohomology spaces actually compute the minimal resolution we started from. So this MP KPQ MV is isomorphic to MP P plus Q with the notation introduced here. Okay, so that's the general theory. So we will not actually work with any graded module, finitely generated module, but we will look at some particular ones which come from a geometric context. Let me, before going to that particular context, let me just say the following, that we can define the Betti table of M seen as a graded S module is the following. So we just draw a table where we put, let's call little k PQ dimension of these Koszul cohomology spaces, and beta PQ was the dimension over C of the spaces appearing in the minimal resolution. So we just draw a table where we put these KPQs like K00, K10, K20, and so on. Then K01, K11, K21, and so on. It might continue. It depends on the module M, but in general it will stop somewhere here. So this is the same as we have beta 00, beta 01, beta 02, Then here we'll have beta 1, 0. Then we will have beta 1, 1. Remember that beta kpq is the same as beta p plus q. So we actually have to add this up. So beta 1, 1, then beta, let's see, this is 2, 1. This is 1, 1, 2, I guess. Is this correct? Beta 1, 2, yes, thank you. Beta, and this is beta 1, 3. Okay, thank you. So beta 2, 0, and so on. So we just fill this table in. So it's very convenient to just to specify the dimensions of the spaces instead of and to put them in this table. This is easy. That one is a bit more complicated because we have to remember that we have to add up actually these indices. Okay. So in this notation, in the example at the beginning, the first example, so if x is 3 points in P2, so the minimal, the Betti table is the following. Was so here we had 1, then we had 3 and 2, and nothing else. So I will make the convention that when I have a 0 entry, I'll just put something here. So this standard for S. Here we had these the three 3 points non-collinear. Here we had 3 quadrics and 2 relations between these 2 quadrics. Whereas in the second, in the collinear case, we just had 1. Then we had 1 linear form, no quadric. We had 1 cubic and 1 relation between these two. So in the Betti table, what we can read on a row, so on a row we read the linear relations. On a diagonal, like this, we read quadratic relations. And more we go down, we increase the degree of the relation. So here we had 1 relation. It was linear here, and of degree 3 here. So that was the example. Okay. So what are now the geometric cases we are going to consider? So most of the time we will be looking at the following type of examples. Modules of type S of x, where x was a projective variety in some projective space. Or, and this was pointed out by Green, modules of the following type. We take x a projective variety. We have L a line bundle on x, preferably at least globally generated, if not very ample, or ample and globally generated. we take modules of type direct sum of spaces of sections in the powers of this line bundle. Or just a version of this example. Again, as before, we take f a coherent sheaf on X, and we just consider this module H naught X, and we can just plug F in here. So these are all the examples we will be considering in the sequel.
Between the first and the second case, because the second case you do not assume it's ample, very ample.
There is a difference. So these do not coincide if X is not projectively normal. So that's the integral closure of this one. So actually, that's more the classical point of view, to look at homogeneous coordinate rings. But then Margarin came and said, well, maybe this one is more interesting. Of course, in the projectively normal case, it's the same. But in the general case, probably this encodes more geometric information than the previous one. And this is actually, that's actually true. He was right. We will see. Okay, so let me just give a definition. This is due to Mark Green. Of course, people knew about Koszul cohomology a long time before Green, but Green was the one that put this in a geometric context. And his motivation was not actually coming from computing minimal resolutions, as I said, but he tried to find new tools for attacking Hodge theoretic problems. Okay, so X is a complex projective variety. As before, L is a line bundle on X. V is just a space of sections, probably not the whole space of sections. And F a coherent sheaf. Okay, and we introduce K, P, Q. So it depends on integers P and Q. And now it depends on X, F, L, and V. That might look a bit spooky, but many things here will disappear. Actually, we will see that in a moment. So that's the cohomology at the middle of the complex. And now we have the Koszul complex, wedge P plus 1 V tensor H naught X F LQ minus 1, wedge PV tensor H naught X F tensor LQ, wedge P minus 1 V tensor H naught X F tensor LQ plus 1, where the first map and the second is given similarly. So this is just is given as before. I'm not going to repeat it. Okay, and now we have the convention. So if it's just to ease the notation a little bit. If V is the whole thing, we just forget about it. And we write KPQ XFL. So that's the first convention. The second one is if F is trivial, then again we drop it and write KPQ XLV if we have a V, or KPQ XL if V again is the whole thing. So the notation KPQ XL stands for the case F is trivial and V is the whole space of sections. Okay, and before ending the first part and taking a short break, we we have now introduced some cohomology.
Sorry, what is HCO already? Is V?
Yes. So in general, V can be taken a proper subspace, just a subspace of sections, not the whole thing. But if it's the whole thing, we just don't mention it. If the linear system is complete, we just don't introduce it in the notation. And, oops. So, actually, this cohomology theory behaves very nicely. In many ways, it behaves like usual cohomology, and we will see that there is actually a relation between the two. And the first nice feature of this cohomology is the following: is semi-continuity. Right? The usual cohomology of coherent sheaves is upper semi-continuous. So if, for example, we have the vanishing of some Koszul cohomology group will happen on some Zariski open set, and it's the same here. So that's semi-continuous, which means the following: if we have f x to s a flat morphism, flat projective morphism of schemes S integral everything I said before also is true for schemes, not only for, we can take X to be just a projective scheme instead of a variety. We don't actually need X to be reduced or whatsoever. But we need projectivity. So we have L, a line bundle on X, and we assume that HI of L, so X, little s, this is just the fiber, and LS are constant for all I. That's not very hard to realize, because it will be, so these HIs will be constant on some non-empty Zariski open set. So up to shrinking the base scheme, we can assume that this is, and also for one case which we will be interested in, like if X, S are all curves, this is automatically realized if H0 is constant, because of Riemann-Roch and the fact that this is flat. So that's not very restrictive, this condition. But if we have this, then the function which associates to any S the dimension of KPQ, every KPQ, XS, LS, is upper semi-continuous. So this behaves very nicely, and we will see in a moment that it's not the only feature which is shared by this Koszul cohomology and the usual cohomology. Okay, so let's have a 10-minute break.